All right, elastic collisions in 1D. Or in one dimension. Okay, we would imagine having a couple different particles moving in different ways, headed along a common line. So we'd have a V1 initial and we'd have a V2 initial for our mass 1 and our mass 2. After the collision, something will happen, and we'll end up with the masses moving in a slightly different way. So now we'd have let me draw this a different length. A V1 final and a V2 final. Mass 1, mass 2. All right, what can we say for sure? Well, we can say that mass 1, V1 initial plus mass 2, V2 initial is equal to mass 1, V1 final plus mass 2, V2 final. We can also say something about the kinetic energy because it's conserved. So we can say 1/2 m1 v1 initial squared plus 1/2 mass 2 v2 initial squared is equal to 1/2 mass 1 v1 final squared plus 1/2 mass 2 v2 final squared. This is the second time today the air conditioning has run. It would have to happen when I'm recording, of course. All right. We can actually do a lot with this. If we're given mass 1, mass 2, V1 initial, and V2 initial, we can use these two equations to find V1 final and V2 final. But it takes a lot of algebraic work, and if you never see it done for you once, you don't really figure it out very easily. There's a tendency to jump into a quadratic approach right off the bat, but dealing with quadratic equations can be quite a pain. So the first thing we want to do is cancel out the 1/2 everywhere in the kinetic energy equation, because it's just kind of hanging out there and being trouble. And since it appears in every part, it doesn't really matter. I'm going to label the momentum equation 1 and the kinetic energy equation 2, and we are going to manipulate these. First thing, we're going to take equation 1 and take mass 1, everything with mass 1 to the left, and mass 2 to the right. We're going to follow up doing this by doing the exact same thing with the kinetic energy equation. So m1 v1 initial, that can stay where it is. We'll subtract the m1 v1 final over. On the other side, we'll be left with m2 v2 final, and we'll subtract the m2 v2 initial over. Last thing I want to do right now, we'll factor out the mass. So mass 1 v1 initial minus v1 final as a quantity equals mass 2 parentheses v2 final minus v2 initial. Same thing for the second equation. So now we'll have m1 v1 initial squared minus m1 v1 final squared equals m2 v2 final squared minus m2 v2 initial squared. And we'll factor the m's out. So m1 times parentheses v1 initial squared minus v1 final squared end parenthesis equals m2 parenthesis v2 final squared minus v2 initial squared end parenthesis. These equations will become 3 and 4 respectively. And here is the trick. Here is the thing that gets rid of the quadratic. This is the thing you've got to remember. Take equation 4 and divide it by equation 3. So we'll have m1 parenthesis v1 initial squared minus v1 final squared equals m2 parenthesis v2 final squared minus v2 initial squared in parentheses, all over m1 parentheses v1 initial minus v1 final in parentheses equals m2 v2 final not squared, whoops, parentheses v2 final minus v2 initial in parentheses. And you notice the mass cancels out. Also, the top is the difference of two squares, a squared minus b squared. Well, a squared minus b squared factors into a minus b times a plus b. So we can write this again as v1 initial, v1 initial minus v1 final in parentheses. So parentheses v1 initial minus v1 final in parentheses, start a new parentheses, v1 initial plus v1 final in parentheses equals v2 final, parentheses, v2 final minus v2 initial in parentheses, begin a new parentheses, v2 final plus v2 initial, and they're all over on the one side, v1 initial minus v1 final, and on the other side, divided by v2 final minus v2 initial. You notice the subtraction terms cancel. We get equation number 5, the one we need, which says v1 initial plus v1 final equals v2 initial plus v2 final. All right, what we're doing here is coming up with an equation that solves for v1 final in terms of masses and the initial velocities. We're going to use this with equation 3 now. Actually, we might want to go all the way back to equation 1. That may be the simplest. So what we're going to do is solve this for v2 final. v2 final is equal to v1 initial plus v1 final minus v2 initial. And we're going to substitute that into our first equation. So we're going to get m1 v1 initial plus m2 v2 initial equal to m1 v1 final plus m2 times the quantity in parentheses v1 initial plus v1 final minus v2 initial. Okay, this is just a few steps of algebra away from being done. So we have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus, you can see when we factor this in, m2 v1 final. Then we have a plus m2 v1 initial and minus an m2 v2 initial. All right, we're going to keep the two terms that have v1 final in them on the right for now and move everything else over. So we'll have m1 v1 initial. I'm then going to take the m2 v1 initial and subtract it. So m1 v1 initial minus m2 v1 initial. Plus, we have an m2 v2 initial. On the other side, we have a minus m2 v2 initial. When we move it over, we'll add it. So we get a 2 m2 v2 initial equals v1 final times the quantity m1 plus m2. This pretty much has it, so v1 final is equal to m1 minus m2 times v1 initial all over the sum of the masses m1 plus m2 plus 2m2 v2 initial over m1 plus m2. This gives us one of the two solutions we're looking for. From here, you'd have to find v2 final, but you can take advantage of equation 5 rearranged to do so. So v2 final would be equal to v1 initial plus v1 final minus v2 initial. You'd substitute in for the v1 final and simplify. That takes a fair bit of work, if I'm being completely honest about it. How long are we into this? Almost 10 minutes. I feel like I should probably let you figure this out for yourselves, but m1 v1 initial plus m2 v1 initial minus m1 v2 initial minus m2 v2 initial. That's creating the common denominator. Okay. At this point, we'll bring in the rest plus m1 minus m2 v1 initial plus 2 m2 v2 initial. All right. Collect like terms. All right, so we have an m1 plus m2, but we had an m1 minus m2. The m2s are going to cancel. We get a 2 m1 v1 initial still remaining for that term. We have a minus and a minus. So it looks like we get a plus m2 minus m1. So that'll take the 2m2 down to m2. This will minus an m2. All right, and then we're still over m1 plus m2. And that gives us our v2 final. Do you have to know how to do this on a test? Well, it took me 12 minutes. I give you a budget of about a half an hour per problem. Fair? So, you will have to know how to do this. You will have to understand the trick. You should understand the proof. Am I going to ask you to do it on a test? No. But I reserve the right to give you a problem that is elastic where either v1 initial or v2 initial is 0. That simplifies the process of deriving this by about 4 or 5 minutes. So you do want to be able to do this. I may ask you to do a related but simpler problem. You're going to want to think on it. Make sure you spend some time to understand this. All right, that's going to be it for what happens with 1D elastic collisions for the most part. Oh, I take it back. We're going to go to 15 on this one. There are some cool observations we can make from this. What happens if the masses are equal? If the masses are equal, well, you may start with a v1 final and a v1 initial and a v2 initial, but well, the v1 initial doesn't contribute at all to the v1 final, and only the v2 does. So if masses are the same, if masses are same, we find the masses exchange their velocities on colliding. That's pretty neat. Okay, another interesting result is what if one of the masses is much, much larger than the other? So what if m1 is 100 times m2? Well, the thing you'd find out is that if m1 is much, much larger than m2, then mass 1's velocity is hardly changed. But mass 2 changes a lot. This can actually be used to do really crazy things, and if we have time in class, I'll try and show you a demonstration where you drop basically a small ball like a tennis ball while it's on top of a bigger ball like a basketball. And what ends up happening is you absolutely launch the lighter ball. It's pretty cool. You can end up really launching the ball if you set the circumstances up right, to the point where we'd want to do the demonstration outdoors to avoid hitting the sprinklers inside of classrooms. All right, it's a fun thing to examine what happens with different values thrown into these equations, and it's cool that we can come up with an exact result for a situation like this. For the inelastic cases, it's nowhere near as fun to play around because we only have one equation to solve the one-dimensional motion there, which means we can really only deal with one unknown. All right, that's going to do it for this video. I'll see you in the next one.